Okay, so now I'm going to pick up on the separation of variables algorithm. Where we ended before, we saw that uk of xt is equal to bk e to the minus k squared t sine of kx. These are called product solutions because, well, it's a product of solutions. So product solutions. These are product solutions because they're a product of solutions. And so now we want to add these solutions up to get the solution to this problem. In other words, we want to make the following, or ask the following question, I guess. I'm not going to claim anything yet. Or just, what if it would be very nice if we could write our solution u of xt is equal to some linear combination k equals 1 to n of these product solutions. bk e to the minus k squared t sine of kx. Okay, what if we could do that? That would be very good because we have an explicit formula for the solution. I mean, not as explicit as kind of things that we've seen before, but we're not always going to get very nice closed form explicit solutions for these equations. In fact, most of the time we won't. So let's ask ourselves a question. If we can do this, so if, big if, we haven't explained why we can do this. So if we can do this, what are the bk equal to? So if we can do this, what are the bk equal to? Okay, well, so let's try to think through this. Notice there's one piece of information that we haven't used yet. It's this boundary value. And notice if you plug in t is equal to 0, this expression gets a lot simpler. The exponential term goes away, and we're just left with the sine terms. So u of x0 is equal to the sum k equals 1 to n bk sine of kx. Okay, and now we're looking at this, and if you remember from linear algebra, if I write a vector as a linear combination of orthogonal vectors, there's an easy formula for that bk there. Okay, we're going to use something similar. Remember in the previous video I talked about inner products and integrals. The sine functions are going to turn out to be orthogonal with respect to this integration. So what I'm going to do is the following. I'm going to look at the integral from 0 to pi of f of x times sine of Lx dx. And I'm going to replace my f of x with u of x0. So in other words, this sum here. So this is going to equal to the sum from 0 to pi. Okay, my f, we're going to have this sum. I said integral from 0 to pi. I said sum, I meant integral. The sum k equals 1 to n bk sine of kx. That's my f of x. This is f of x. And then I'm going to multiply by the sine Lx function. I'm trying not to get in the way of the board, but with the cameras this far close, the angles are such that wherever I am, I feel like I'm in the board here. Okay, now what I can do, this is a finite sum. The sine functions are all bounded, no problem at all with exchanging the sum and the integration. And what I'm going to get now is the sum. That's a defunct sigma there. I'm going to get the sum k equals 1 to n bk, and then the integral from 0 to pi sine of kx sine of Lx dx. Okay, so here's what I want you to do. I'm not going to do this computation. I want you to compute this. K and L are integers. I want you to compute this. Now the way I would compute this is by using Euler's formula so that I can just integrate exponential functions, which are easier to integrate. You do it however you want to. But this, however you do it, okay, I'm going to write down what it is. Maybe you want to pause and do this on your own. Okay, this is going to be equal to pi over 2 if k is equal to L, and it's going to be equal to 0 otherwise. Okay, so in other words, if I look at each term of the sum is only, like the term in the sum is only, each term of the sum is 0 as long as k is not equal to L. So the only non-zero term is going to correspond to k is equal to L. In which case we get BL times the integral from 0, we get BL times pi over 2. So I have this on the left-hand side, this on the right-hand side. If I multiply everything by 2 over pi, I'm going to have 2 over pi here. I'm going to have 2 over pi here. I'm going to have 2 over pi here. And of course, this 2 over pi goes away. And so BL is equal to 2 over pi times this integral here. Okay, so copy this down. BL is equal to 2 over pi times this integral. So then this tells us BK now I'm going to change back to the k index. So BK is equal to 2 over pi times the integral from 0 to pi f of x sine of kx dx. Okay, so let's address this question now. When is this possible? Let's at least think about answering this question. So when is this possible? Well, notice it all came down to whether or not we can write our initial condition f of x as a sum k equals 1 to n bk sine of kx. If we could do this, then all of our work follows and we could write our solution as a linear combination of these product solutions. Okay, now this is almost never true. This is almost never true. But what is true is if we replace the n here with an infinity, this is almost always true. Except now, we have to be careful about what this means. What does this mean? What does equality equal to? I have f of x is equal to something on the right-hand side, but the something on the right-hand side is really a series of sums, a sequence of sums. So remember how this is defined. This is defined as something like the limit as n goes to infinity of these partial sums. Okay, well now we're going to get a little confusing here because we've got an x variable and an n. This is a sequence of functions, so you might remember like Taylor polynomials. Taylor polynomials are a sequence of functions that approach a function. This is something similar is going on here, but in what sense does this sequence of functions approach this sequence of functions? What we would want is that this limit is just true for every value of x, that it holds pointwise. But that's not always going to be the case. So the next best thing is to say, well, it's going to hold for almost every value of x. So let me just illustrate one obstacle and why these two things, like why we can't have a pointwise inequality. Well, notice if I plug in x is equal to 0, I get 0 here on the right-hand side. And if I plug in pi, I get 0 on the right-hand side. But for a generic f, not all f's satisfy f of 0 is equal to 0, and f of pi is equal to 0. Okay, so what we will see is that for functions like that, this sequence won't converge to f everywhere. It'll probably only converge, at best, it will only converge to f at the interior. So just as an example of what I'm talking about here. Let's just say f is equal to the constant function 1, going from 0 to pi. If you look at the partial sums are going to look something like this, and then back down there to pi. Okay, and actually, there's going to be quite a bit of stuff over here, typically called Gibbs phenomenon. But as n goes to infinity, all of that settles down, and it converges to 1 when x is bigger than 0 and less than pi, and it converges to 0 there, if I just look at the constant function 1. Anyways, so what we're going to assume for this week basically is that in any appropriate sense, or that in some, not any appropriate sense, in some appropriate sense, this is true. And then in the coming weeks, we'll actually nail down what exactly that means. Actually, next week we'll nail down in what sense is this true. And also we'll see a little bit later, we're going to replace the sine functions with the cosine functions. Okay, that's it for this video. That, I guess, so I didn't mention over here, step 4 and 5 are somehow together. The book kind of puts them together. Basically, just finish, so find the BK coefficients. I'll just summarize it like that. I do want to mention one thing. You might be wondering, why am I using BK coefficients? Like, why am I using the letter B and not the letter A? Traditionally, the BK coefficients go along with sine, and AK coefficients go along with cosine. Just a convention. Okay, so now I think I'm done with the video, and I think I'm done with this first boundary value problem. I think, look at the next boundary value problem. This part's different. Go through this and see if you can get what we're going to get. Okay.